It's give you the delta G. So delta G is equal GV times V. Then um, I want to introduce you the surface energy of your material. So with your liquid, any material have a surface energy uh, with the vacuum or with the liquid or with the air. Whatever is your surface is the amount of energy is formed by increasing the surface. So if you increase the surface of your material uh, in amount of A, then your delta G increase by G delta G. Then uh, then lambda equals to uh, the delta G over A. Okay. If you have, you can have surface energy in water. If you have a liquid in water, a solid in water, the surface energy between your particle, whatever is your solid particle, with the liquid medium, is called surface energy of your particle with water. Uh, for in for measuring the surface energy, you can do this contact angle measurement. So the contact angle measurement give you this, the if you draw it as a vector, basically surface forces, the surface energy of for in here, for example, copper sulfide with air is called uh, it's called gamma A, and then gamma to air. Then if you have the water to air is with the red, gamma to air. And if you have solid to your liquid, okay, if you have solid to liquid, then you have gamma, mm, uh, gamma copper sulfide to liquid, S to water. And if you consider these three as vectors, these vectors are in equilibrium. So the the integral or integration of this summation of this vector should be zero because your liquid is standing on the surface of the material. Okay, so as higher surface energy you will have, then the, the angle, the alpha angle will be higher because these two surface energy, the red and green, should sum to each other in the way that they equalize to this surface energy, the surface energy of solid and water. Okay, so let us start to calculate the amount of the g function change by changing or by size of your radius of your particle. Imagine your cluster or your particle is grown spherically, so it's a sphere, just like a earth, or just like a ball, or just like an orange is a spherical. Okay, so the volume of this sphere is 4 over 3 pi r power to 3. The area of this sphere is 4 pi r power 2. So the volumetric G is minus delta GV delta GV time volume, and the surface energy is the delta G over A. So the G function is GV 4 over 3 pi R3 plus gamma 4 pi R2. Okay. So this is the G function over R. It has two parameter GV and gamma. Then we have 2 points in this. If you plot the G function over with respect to R, respect to radius of your particle, we have 2 points. At R star, the the it's in the maximum. Uh, R it's in the cluster size or nuclide size of your particle. It's dg over dr is equal to 0, and at r0, which is the size of your nanoparticle, equilibrium size of your nanoparticle or particle, is the g function is equal to 0. So we start to calculate the derivative of g function over r. Dg over dr equals to, we get the simple derivative from these functions, and in the end what we get is dr over dg over dr equals to minus g 4 over 3 pi d r3 over r plus gamma 4 pi dr2 over dr. Okay, and dr3 is equals to 3r2 plus 2r. Okay, then at r equal to r star, dg over dr, the first derivative of g over r is equals to 0. So then we put this into 0 at g star or r star. Then we continue our calculations. Then minus g v times r star plus 2 gamma equals to 0. Then 2 gamma equals to r star gv, and r star equals to 2 gamma over g volumetric g. So basically we can understand what is the size of the critical size of your particles, nuclear size of the particle. Then we consider the stable size of particle, which r0, at r0 g equals to 0. Then we put it at 0, g equals to minus g4 over 3 pi r0 times 3 plus gamma 4 pi r0 power 2 equals to 0. And then we cancel out some of the parameters, and in the end r0 equals to 3 gamma over g. So it's the equilibrium size of your particle. So at this size, your particle is stable. It does not grow faster anymore. It's in the equilibrium. So then we should play with the thermodynamic at the next level. So these are some calculation. We should change some of our thermodynamical variation, like temperature or something, to change gamma and uh, G. If we can control gamma and GV, small g, then we can control the size of our particle. So let me show you the next slide. The various parameters. We want to work at the close to equilibrium. So if we want to work at the close to equilibrium condition, we need to play with the temperature. So and temperature and uh, concentration of our ingredients. Uh, Basically, if you have a reaction A to B reaction, so you have concentration of A and concentration of the B as a result, and your ingredients and results. So B is your results and A is your ingredient. And at the standard condition, the delta G is equals to how much? Uh, Delta G zero, which is called delta G of standard condition at the 1 molar concentration, plus RT L and Q. What is the Q? Q is the constant of your reaction. Is the uh, is the ratio of your results, concentration of your results over the concentration of your ingredient. So imagine you have a reaction which at the standard condition, at normal temperature, it has most of the condensation, most of the solidification and condensation reaction have delta G below zero. So delta G is at the standard condition that their delta G is zero is lower than zero. So if your delta G zero is lower than zero, is a minus. So you need to increase the, the other part of your equilibrium, RT, L, and Q, in a way that you increase that delta G at that condition become close to zero. So if we can call it in this way, or we can say it in this manner, that if you want to if you want to synthesize a nanoparticle, you need to increase this part, RT, L, and Q. Okay? RT, L, and Q, if you want to increase it, RT, L, and Q, you need to know that for increasing our RT, L, and Q, R is positive, T is always positive because we don't have the minus absolute temperature. Always the absolute temperature is positive. So, and the ratio of results over the ingredient A should be above 1. What it means? If it's below 1, the L and Q become minus. So you want to the summation of these results become around 0. Why we want to have this around 0? Because we want to reduce the reduce the size, reduce. I'm sorry. We want to reduce the delta G as much as possible. If we saw or vessel, if we take our vessel as a system, we want to have the delta G of not only one particle. In the previous slides, we calculate the delta G of the whole one particle. Okay. In this slide, we are to see our system, the whole jar of our particle or whole vessel of our particle is considered. Okay. Now we calculate not only one particle. We want to see the system, the lots of particles, not only one particle. If we want to see the system, not only one particle, then we need to take to account the temperature of the condition, the vessel, and we need to consider, just let me, thermodynamical variation of our particles. We need to take it as a system, not, we cannot control the temperature of one nanoparticle. We have a system, a jar, a vessel, a flask in the lab. Then we can control the temperature. You know what I mean? In the previous lecture, in the previous talk, we consider the effect of temperature and parameters in the microscopic level, on a tiny levels. In here, we are seeing in the macroscopic level, not microscopic level. In here, we see the microscopic system, the large system, the whole uh, beaker of, or the whole glass of nanoparticle. In this condition, the delta G is controlled by the concentration, initial concentration of your ingredient, concentration of your resulting nanoparticle, and the temperature, and also the delta G at the standard condition. So the delta G at the standard condition is the one you have it at the room temperature and the concentration of 1 molar. So for reducing the delta G close to zero, so you want to control your size in the macroscopic level, then you need to decrease, you need to increase the temperature, because the delta G zero is most of the time is minus. You need to increase the temperature, and you need to set the Q above 1. Then the delta G become close to 0. So then you need to increase the temperature of your system. You need to decrease the concentration of your ingredient material. This is very important. This is very important. So that's why when we are synthesizing nanoparticle from the bottom to top, from the ions to nanoparticles, we need to increase the temperature. So, and reduce the concentration of initial material. This is absolutely important. If you do not do that, the speed of your reaction goes very high. You won't get the nanoparticle. You will get a huge amount of powder. So basically, this is what we do. This is what we done in the lab. So let me change it also here. we have two major conditions for increasing the temperature. First, you can start from the solution based on water and increase your temperature. It's called hydrothermal synthesis process. And secondly, you can have secondly you can have a solvent containing your ingredient and nanoparticle, and you increase the synthesis temperature also there. So you have two conditions: the 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 solvothermal and hydrothermal condition. So hydrothermal condition is the condition that you have a solution of your ions or ion ingredients in the water, and you reduce down the ingredient concentration. And secondly, you are working with the solvent, which you dissolve your particles, and you increase the temperature. By doing these two, you will have control of your system. So in the system level, in the large vessel level, you you set the volumetric condition around zero, the 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 delta G around the zero at the macroscopic level. Okay. If you don't do that, if you leave it like that without, uh, if you do it without controlling of your temperature, probably you will result into large powder, not the nanoparticle. You look like you're looking. We all know that if we don't control our system, or we don't control our precipitation condition, or particles get very large. They are not nanoparticle anymore. Okay, we all know that. So to do that, we need to control what? We need to control the temperature and concentration of our ingredient, and then we can control the growth of or nanoparticle. And that's what is done usually. That is what is done. Uh, and if you work with the water, it's called hydrothermal process. And if you work with the solvent, it's called solvothermal process. There are two main routes of bottom to top approach. We will discuss this in in very we will discuss it in the details on the next session. We will cover both hydrothermal and solvothermal precisely, and what is the differences of the hydrothermal and solvothermal, and in which method you can get the larger particle, and in which method you can get a smaller particle. We will study both of them, and what is the advantage and disadvantage of uh, each of these methods. So if you have any question, please let me know. I will answer. Okay. Do you have any question?